We often imagine an advanced civilization commanding the power of an entire galaxy. But in 2025, humanity saw real progress, yet incremental in the energy numbers. Fusion experiments in Europe sustained plasma for over 20 minutes, a record that hinted at fusion's practical future. Quantum computers and AI systems opened tangible pathways in energy modeling and grid optimization, though none of these by themselves directly raised our output. Still, our place remains roughly 0.73 to 0.74 on the fractional Kardashev scale. Why measure progress this way? And what did the original architects of this idea have in mind? A scale born in the Cold War. During the 1960s, the geopolitical atmosphere was defined by nuclear weapons, the early space race, and a deep conviction that power, both political and technological, rested on controlling energy. In this climate, Soviet astronomer Nikolai Kardashev asked a provocative question: how might one rank civilizations, not by culture or ideology, but by the sheer scale of energy they could command? His proposal was simple in structure but revolutionary in scope, and it became known as the Kardashev Scale. The framework he introduced in 1964 divided societies into three basic stages. A Type I civilization would be one that could harness and direct all of the energy available on its home planet. A Type II civilization would capture the entire output of its star, perhaps through massive orbital constructs designed to channel solar radiation. A Type III civilization stood on the unimaginably vast scale of a galaxy, with its energy network stretching across billions of stars. Kardashev's purpose was not entertainment or science fiction, but a scientific tool for thinking about extraterrestrial intelligence. If astronomers ever intercepted signals requiring more energy than modern Earth could generate, that detection alone would suggest a civilization positioned far higher on the ladder. Underlying the scheme was a physical reality. Energy unlocks capability. Greater reserves allow rockets to escape gravity wells, factories to scale without limit, and even hypothetical megastructures to function. It made energy a logical and measurable yardstick for classifying progress. Technologies of the mid-20th century made this argument vivid. Nuclear plants hinted at power beyond fossil fuels. Early satellites depended on rapid bursts of high energy to reach orbit, and atomic weapons underscored that mastery over energy was mastery over destiny itself. Against this backdrop, Kardashev's energy-based framework felt both rigorous and intuitive. One of the reasons the scale endured is its clarity. Kardashev did not frame the categories in cultural terms that might prove subjective or ambiguous. Instead, he established concrete thresholds that could be quantified. Entire planetary outputs, stellar totals, or galactic sums. And though these numbers were, and remain, astronomical by human standards, the neat division gave scientists and futurists a simple reference to discuss not just alien civilizations, but a theoretical map of humanity's own future. Almost immediately, scholars realized that three fixed points were too coarse to describe a civilization mid-journey. To address this, later thinkers introduced fractional levels, allowing humanity's current development to be plotted as something like 0.7, 0.8, or 0.9, steps between Type 0 and Type I today. When analysts estimate our position around 0.73 or 0.74, they rely on this refined approach. Fractional scoring made the Kardashev scale not just a lofty abstraction, but a practical tool to judge progress at finer resolution. Context is important here. When the scale was proposed, satellites and post-war space programs were still in their early stages. Nuclear energy was just beginning to spread to civilian electricity grids. The moon landings were on the horizon rather than in the past. Against that backdrop, imagining humanity reaching planetary scale control of energy within a century might not have seemed entirely fanciful. But over the 6 decades since, achievements in computing, communications, and exploration have far outpaced actual growth in total energy control. Grand advances have not yet translated into the gigantic energy totals needed to advance even one full rung on the scale. This is where another layer of tension emerges. Society visibly transformed in ways Kardashev himself could scarcely have predicted. Global networks, artificial intelligence systems, reusable rockets, telescopes capable of probing exoplanets. Yet the actual energy tally that matters on his scale leaves humanity still in the subplanetary range. The contrast is sharp. Our world feels saturated with technology, but the raw energy captured falls far short of even the first complete category. The scale thereby imposes a sobering perspective, reminding us just how demanding those thresholds truly are. Instead of discarding the model, many scientists, writers, and futurists began to expand it. Subsequent versions propose civilizations even greater than galactic in scope, with speculative types IV or V harnessing cosmological or intergalactic resources. More practically, refinements have also tried to blend Kardashev's focus on quantity with broader metrics: efficiency, coordination, and sustainability. For example, some envision a civilization that uses clever systems to extend limited energy supplies as comparable, in practice, to one that simply consumes more without regard for waste. Others argue that the ability to sustain progress without destroying planetary ecosystems is itself a form of technological maturity. At the same time, the method of applying the scale to searches for alien life has broadened along with astronomy itself. In the 1960s, the focus rested on radio telescopes. Powerful signals would correspond with enormous energy budgets, making advanced civilizations theoretically easier to detect. Today, detection strategies range well beyond radio. Astronomers now examine stars for unexplained excess infrared light that could indicate waste heat from giant energy-harvesting structures, assess atmospheres for industrial chemicals unlikely to form naturally, and look for orbital arrangements that suggest artificial intervention. Each approach still relies implicitly on Kardashev's insight that large-scale energy use leaves signatures visible across interstellar distances, but brings new techniques to bear on the same logic. The value of this framework is not that it captures every dimension of progress. Culture, ethics, knowledge sharing all matter in their own right. Its staying power comes instead from grounding the conversation in the hard limits of physics. Any society, no matter how clever, cannot advance beyond what its energy reserves allow. From campfires to nuclear grids to possible Dyson-like constructs, the relationship between power control and civilizational reach is direct. That is why the Kardashev Scale, conceived in a Cold War setting, remains a centerpiece in modern discussions about long-term futures and cosmic possibilities. And while the scale continues to spur speculation about what humanity might someday become, it also places present-day reality in stark relief. As of 2025, the numbers that plot our position show a civilization still below the first true step. That reality presses an important question. If technology surrounds us in every direction, why do the core energy figures suggest progress remains so incremental? The answer lies in understanding what those figures actually mean for us today, where humanity really stands in 2025. If you stop to consider humanity's position in 2025, the contrast is hard to ignore. In daily life, the technologies surrounding us feel extraordinary. Artificial intelligence runs entire infrastructures, rocket launches are routine, and digital communication is instant across the globe. Yet when measured against Kardashev's framework, we remain below even the first rung of a planetary scale civilization. The scale reminds us that while our world appears advanced, the yardstick of total energy control tells a more modest story. How much power does humanity command right now? Depending on which dataset you use, the figure falls somewhere on the order of 18 to 22 terawatts of continuous power, equivalent to running tens of billions of laptops or millions of industrial plants at the same time. To give a benchmark, in 2018, the International Energy Agency documented around 18.4 terawatts of global primary energy use. And since then, demand has risen steadily with economic growth, electrification, warmer climates, and digital infrastructure. Rounding toward the higher end gives the sense that humanity now manages a couple dozen terawatts at most. It is an impressive sum by human standards, enough to light cities, move continents worth of vehicles, and keep the modern economy functioning. But the comparison that Kardashev invites is not with our own history. It is with what a planet like Earth offers in total. By that measure, we still draw only a thin fraction of the energy Earth could in principle yield through its solar influx, winds, oceans, and core. That reality places us around 0.73 to 0.74 on the fractional Kardashev scale. The math behind it is not especially complicated. Analysts compare humanity's actual global energy budget against the theoretical energy available from a planet-wide capture of sunlight and other flows. On that continuum, one indicates a society fully at type IR score, still below 3/4 of the way, reflects a civilization that has made huge strides relative to centuries past, yet remains firmly in the pre-type I category. Many researchers describe us as a type 0 civilization. The phrase isn't an insult. It simply signals how vast the remaining climb actually is. This is the paradox of the present moment. We feel surrounded by breakthroughs, but the raw numbers move upward only gradually. Renewable deployment continues to scale, with solar and wind now surpassing hydropower in global contribution. Nuclear power has been stable for decades, with only modest additions. Fusion experiments are finally holding plasmas longer than before, and grids increasingly incorporate cleaner sources. Each milestone makes headlines, but when combined the totals nudge our place on the scale only slightly higher each year. Growth is clear, but not exponential at the order needed to push from fractions of type I into the real threshold. The sense of slow motion has a history. In the 1960s, some optimists expected nuclear power alone would be sufficient to carry humanity neatly into planetary scale energy within a few generations. Instead, nuclear power leveled out, partly due to cost and partly due to environmental and safety pressures. Renewables stepped in, and between 2021 and 2024, solar capacity doubled again, with wind not far behind. But even as those numbers climb fast relative to recent decades, when stacked against the benchmark for type I, around 10 quadrillion watts, or 10 million gigawatts, they reveal how small the slices remain. Humanity commands terawatts, but Kardashev's first rung demands quadrillions. Seen from that angle, all of today's marvels, AI-optimized economies, orbital launches, robotic probes, operate within what is still a modest energy budget. For scale, an average nation may handle hundreds of gigawatts, humanity as a whole around 20 terawatts. Type I would mean advancing orders of magnitude further. To move from trillions of watts into quadrillions requires leaps rather than mere growth. The categories on Kardashev's ladder emphasize that moving from one prefix to the next, tera to peta to exa, signifies entire revolutions in capacity, not incremental upgrades. So why has progress felt steady yet insufficient? One factor is that consumption is unevenly shared. While advanced economies push rising per capita use, many regions still lack even reliable access to electricity. Kardashev's scale doesn't account for fairness. It only tallies totals. But in practical terms, uneven distribution slows our momentum as a species. It means global society is not yet pooling its abilities into a shared upward push, instead developing in fragments. Another factor comes from the environment itself. In principle, we could expand power use much faster if we leaned heavily on fossil reserves. But doing so would damage climate and ecosystems to the point of threatening civilization's foundations. The climate crisis creates limits that Kardashev's theoretical ladder never addressed. As a result, progress toward Type I requires not only scale but sustainability. Solar, wind, hydro, nuclear, and potentially fusion represent ways forward, but transitions built around them unfold at a cautious pace compared to the raw acceleration possible in the absence of environmental constraints. In practice, climbing the scale slowly but stably is a necessity, not a failure. This leaves humanity in 2025 with a peculiar standing. Our global energy system is bigger and cleaner than ever. Renewables reach record shares of electricity generation. Laboratories flirt with new frontiers in plasma physics, and AI helps optimize grids. Yet the distance from 24 terawatts to 10 quadrillion watts is still immense. Each year's achievements matter historically, but the movement of our decimal place on the Kardashev scale remains small. That persistence of fractionality is both humbling and motivating. It raises an obvious question. What kinds of advances could actually move the needle? Would more nuclear reactors accelerate the growth needed? Could novel grid designs and AI-driven efficiency shorten the climb? Or is the real key a leap into entirely new modes of power, something that fundamentally expands the scale of human energy capture? These questions form the backdrop of our next steps, because the challenge before us is not merely keeping pace. It is breaking out into orders of magnitude greater control. And this is why one technology, long relegated to promises about the future, has again entered the spotlight. In recent years, it has begun to show shifts that suggest the timeline to Type I might be shorter than once imagined. Fusion's quiet breakthroughs. Why has fusion carried the reputation of being forever the energy of the future? The answer lies in its history. For decades, scientists promised that humanity was on the cusp of recreating the sun's power on Earth, only to postpone the timeline again and again. Each generation heard forecasts that commercial fusion was 30 years away. Each watched that horizon slip. But in 2025, this cycle shifted quietly. New results from European and US experiments demonstrated forms of stability and sustainment that many doubted were achievable outside simulations. These runs did not put fusion on the grid, but they altered the conversation with tangible data. One of the year's highlights came from France. The West tokamak set a milestone by sustaining hydrogen plasma at 50 million degrees Celsius for 1,337 seconds, over 22 minutes. To put that in context, the previous record was just under 18 minutes, held by China's East tokamak. Germany's Wendelstein 7 accelerator also refined its control systems for operating longer at stable conditions, while the retired jet reactor in the UK demonstrated up to 60 seconds of high-quality plasma containment before closing its chapter. Meanwhile, the United States pursued inertial confinement at the National Ignition Facility, where in 2024, laser-driven experiments pushed past earlier ignition numbers with outputs above 5 megajoules. These results, though diverse in method, carried a common theme. Fusion reactions are no longer measured only in fractions of a second. They now persist long enough to test the physics under conditions approaching continuous operation. Records, however, come with context. Every sustained reaction so far has demanded massive input power to achieve ignition. Lab runs still rely on machines the size of stadiums, magnets that consume entire power stations, or lasers that must fire with pinpoint alignment under extreme precision. Net power in the lab remains an event, not a routine. This does not diminish the progress, but it clarifies that the leap from records to usable reactors is enormous. The scale-up is not simply a matter of building more machines. It requires bridging an engineering gulf where materials, costs, and durability all converge. The message is clear when comparing past efforts to the present. For much of fusion's history, plasma collapsed in microseconds, never long enough to answer basic engineering questions. Now sustained runs give scientists a living laboratory. Instead of imagining how plasma turbulence might behave, teams can watch it unfold over minutes and adjust their algorithms in real time. Extending reactions into measurable durations moves the field from theoretical proof toward repeatable procedure. That momentum changes not just the physics but the psychology of the effort. Once a threshold is breached, attention turns to how to scale, not whether scaling is even possible. Still, the obstacles remain steep. Reactors must survive extreme neutron bombardment at full power, which gradually weakens internal walls. They require magnets built from advanced superconducting materials that function at near absolute zero to hold plasmas hotter than stellar cores. They need precision fueling systems to maintain balance while sustaining reactions continuously, not just in brief runs. On top of that, costs tower over every proposal. These machines demand billions of dollars per build, decades of planning, and a global supply chain for bespoke materials. Consolidating these obstacles into a coherent plan for actual power generation is the task ahead. What changes now is not that the obstacles vanished, but that industry, investors, and policymakers can watch real test results instead of speculative projections. This shift matters. Early investors often saw fusion as synonymous with delay. Now, the string of records is convincing private capital to support ventures like Commonwealth Fusion Systems, which plans its first demonstration plants in the 2030s. Governments, too, approach the field differently when milestones arrive on news cycles instead of languishing in research journals. Incremental gains translate into altered funding priorities, as policymakers recalibrate to a reality in which fusion is not an impossible quest, but an area of competitive advantage. The cumulative effect is subtle yet significant. Each new run bends the trajectory toward deployment ever so slightly closer. From the perspective of Kardashev Scale, the meaning is straightforward. Humanity lingers between fractions of type I because current technologies remain constrained by fossil reserves, intermittent renewables, and political resistance to fission. Fusion is one of the few options that could provide planetary scale energy without compounding environmental risks. Its fuels, deuterium from seawater and tritium sourced from lithium, are orders of magnitude more abundant than oil or coal. If reactors become practical, the scale of supply would support centuries of growth while maintaining minimal carbon output. It is not the only technology needed, but it could serve as the backbone for multiplying humanity's total usable energy toward Type I levels. Fusion's progress in 2025 also carried symbolic weight. Successful records change perception. In the 20th century, the Apollo missions showed the moon was not abstract soil, but a place humans could visit. In an analogous way, sustained plasma runs show that controlled stellar fire is not purely notional. It happened under test conditions that can be cataloged, measured, and repeated. That difference reshapes the imagination of planners and industries. Rather than seeing fusion as a dream, leaders must now treat it as a challenge. How to accelerate its move from billion-dollar prototypes toward practical plants. Of course, promise alone does not translate to global change. Kardashev's ladder measures control and deployment, not isolated experiments. Fusion's milestones must grow into networks of reactors capable of supplying whole grids before humanity's score rises meaningfully. That requires improvements in reactor design, building supply chains that can scale, governance to ensure safety, and societal confidence in long-term investment. Yet the crucial fact of 2025 is that fusion is no longer a narrative of endless postponement. It is a technical and organizational problem exposed under real conditions. That distinction infuses the field with a new sense of momentum. Viewed across the broader arc of history, the energy ceiling humanity faces today cannot vanish without breakthroughs like this. Terawatts will not become quadrillions purely through efficiency gains or fossil extension. Kardashev's early categories laid bare how steep the climb is, with records now proving that sustained fusion reactions are within reach. talk of planetary scale power has evidence to stand on. The gap between laboratory and power plant is still immense, but it is measurable, concrete, and more importantly, in motion. If fusion is the engine that promises scale, something else will determine how fast humanity can reach it. The real accelerants may not be found in the reactors at all, but in the tools that guide, predict, and optimize them. AI as the hidden accelerator. Could machines, not humans, be the underlying force that makes large-scale energy control possible? In 2025, artificial intelligence has begun moving beyond convenience applications to become an embedded operator inside critical systems. It now functions at speeds and scales that human engineers cannot match. If civilization's climb toward Type I relies on maximizing energy capture and management, then AI is emerging as the quiet accelerator behind that progress. One of the clearest examples is its role in electricity networks. Balancing a modern grid is no longer a matter of adding and subtracting generation sources. A single national grid must coordinate nuclear baseload plants, flexible gas turbines, hydropower, and rising shares of solar and wind. The renewable fraction is vital, but it introduces uncertainty, because weather and daylight never align perfectly with demand. Instead of relying only on human operators anticipating consumption patterns, utilities now deploy AI systems that monitor and optimize regional grids in real time. These systems process thousands of variables each second, forecast demand spikes hours ahead, and detect faults before they spiral into cascading outages. Each avoided failure preserves stability, which in turn allows networks to absorb more clean but variable generation. Without predictive stabilization, scaling to higher outputs would risk overload. With it, grids can edge closer to the upper limits of their design capacity. Fusion research highlights another role for machine intelligence. Plasmas at fusion temperatures behave with volatile unpredictability, developing instabilities that can end a reaction in microseconds. For decades, human researchers adjusted magnetic controls using models and static assumptions. By 2025, experimental reactors are integrating AI models and control systems that respond to sensor data far faster than any human operator could. Neural networks trained on vast plasma datasets suggest adjustments in real time, helping extend stability during test runs. No system has yet delivered practical energy, but these experiments show that AI is not auxiliary. It is starting to make the difference between a collapsing plasma and one that persists long enough for meaningful analysis. In a field where every additional second of stability opens new learning, the advantage is significant. AI also accelerates discovery in the supporting domain of materials science. Reactors and high-energy infrastructure require components able to operate under radiation, extreme temperatures, and mechanical stress. Traditionally, trial-and-error approaches consumed years to identify new alloys or ceramics with the right resilience. Machine learning compresses this search by scanning through immense datasets of molecular structures, cross-referencing properties, and proposing candidates for lab testing. This shift turns decades of exploration into months of simulation and prototype. Every step forward in materials that last longer inside harsh environments extends the potential operating lives of reactors, turbines, or storage devices that must withstand conditions beyond what current matter can endure. Taken together, grid coordination, plasma control, and materials discovery, AI widens the usable fraction of energy humanity already generates, and simultaneously pushes the boundaries of what new systems can sustain. This is where its role intersects clearly with Kardashev's framework. The scale counts watts, but the effective energy under our control grows when efficiency increases and reliability improves. A civilization that orchestrates its energy with intelligence manages more of its planetary budget than one that allows waste and failure. By raising this effective control, AI helps narrow the distance to Type I without requiring immediate leaps in raw generation. These benefits come with a parallel set of warnings. Critical infrastructure is increasingly dependent on algorithms that few people fully understand, even within the engineering teams deploying them. Energy grids stabilized by AI might be less transparent to human oversight, meaning errors could propagate in ways difficult to diagnose. In fusion experiments, operators rely on neural networks whose decision-making paths are opaque. In materials discovery, models often propose candidates with no intuitive explanation for why they work. This opacity does not negate progress, but it highlights that efficiency gains can outpace human comprehension. A machine-guided climb up the ladder introduces vulnerabilities if governance and adaptation lag behind. The social and economic layers reinforce this risk. Efficiency through AI allows grids to operate with fewer redundancies, but it may displace the workforce that once managed those redundancies. Material discovery acceleration creates breakthroughs but reshapes industries at a speed demanding retraining. Fusion research guided by learning systems creates engagement for physicists, but also shifts intellectual leverage to software models. The net result is that machines increase civilization's capabilities while pressing human institutions to adjust with unprecedented speed. If society cannot match that pace, the benefits come entangled with instability. A reality check is necessary. Kardashev's metric does not account for governance quality, but without stable institutions, greater energy flows serve little purpose. In 2025, debates over AI in infrastructure focus less on whether it works, evidence shows it does, and more on how reliance can be managed responsibly. The shift underlines a pattern. Progress toward higher-scale control is not purely technical. It requires balance between technological reach, social acceptance, and resilience against failures or misuse. None of this diminishes AI's practical momentum. Global demand prediction systems already smooth energy peaks that once forced expensive reserve capacity. Millions of appliances, electric vehicles, and industrial processes are integrated into predictive networks that spread load more evenly. The effect is that grids operate closer to full potential without catastrophic overload. Fusion laboratories now collect longer and richer data from sustained plasmas, because AI-managed control buys them more time before collapse. Materials scientists focus their experiments on candidate compounds selected from thousands of AI-screened possibilities, reducing wasted effort. These examples are incremental, but when multiplied across domains, they accelerate civilization's available energy budget in compounding ways. Seen in this perspective, AI is less a replacement for human effort and more a multiplier of civilization's total output and coordination. It does not invent new categories of energy, but it makes the categories we already pursue work with far greater precision. That influence is subtle in everyday life. Lights that stay on more consistently, devices that manage power consumption invisibly, minor efficiency gains in industry. But together, it represents measurable forward movement on Kardashev's fractional ladder. Humanity will not reach Type I by intelligence alone, but without it, the climb would almost certainly stall. As of 2025, the question is no longer whether AI contributes to humanity's energy future. The evidence shows it already does, in grids, in reactor labs, in design of materials, and in predictive planning. The remaining question is how far this acceleration can carry us before the next bottleneck appears. Energy, after all, is not only about coordination, but also about discovery. To unlock still greater capacity, new forms of computation may be required to solve equations that overwhelm even the smartest machine learning models in use today. That challenge is beginning to converge with another frontier technology, one whose advocates claim it can tackle problems that overwhelm all conventional digital systems. Quantum computing and the energy equation. Quantum computing and the energy equation are increasingly linked in 2025. While the technology does not generate power itself, It is beginning to shape how efficiently humanity can capture, distribute, and extend the energy we already command. The connection may not be obvious at first glance, yet the capacity to model, optimize, and discover faster and at greater scale affects nearly every step of our climb toward planetary-level energy use. At its core, a quantum computer is defined by its qubits, units that differ from classical bits by existing in overlapping states rather than as fixed zeros or ones. This allows a quantum system to represent and evaluate enormous numbers of possibilities in parallel. For highly complex problems, such as optimizing a grid or modeling turbulent plasma, this capacity can unlock insights that classical machines cannot reach within reasonable timeframes. The challenge has always been fragility. Qubits are easily disturbed, errors multiply quickly, and scaling up often creates more instability than progress. In 2025, though, several experiments reported meaningful advances. Research teams demonstrated early error correction schemes where clusters of fragile qubits could be treated as more stable logical units. That step reduced runaway error rates and kept calculations coherent long enough to complete practical routines. At the same time, prototypes edged toward hundreds of physical qubits arranged in usable architectures. These machines remain experimental, but they now perform test runs relevant to real-world challenges, especially in energy systems where optimization and simulation matter most. Energy grids are one of those test grounds. A national or continental grid has to balance countless demand signals and sources at once: industry, households, electric vehicles, batteries, solar, wind, nuclear baseload. The number of possible arrangements at any moment is astronomical. Classical computing handles this with approximations and algorithms that cannot account for every interaction. Quantum machines, even at today's limited scale, have begun processing grid datasets to identify combinations that reduce waste, anticipate mismatches, and improve distribution stability. These are not solutions ready for immediate deployment, but proof-of-concept runs in 2025 demonstrated measurable improvements over classical approaches in simulation. The implications are significant, stretching every generated watt further without needing new physical plants. Another field where quantum computing shows potential is nuclear fusion. Modeling plasma behavior is one of the most difficult problems in modern physics. Minute changes cascade into chaotic turbulence, making it essential to capture particle interactions at extraordinary resolution. Quantum processors, even with their current limits, offer ways to simulate underlying atomic and molecular interactions that remain inaccessible to classical computation. Researchers now use them to explore new materials for reactor walls, superconductors for magnets, or fuel cycle predictions. None of this replaces experiments inside tokamaks or stellarators, but quantum runs help narrow the design space so that laboratory work begins closer to viable solutions. That reduction in trial and error could shorten the timeline between demonstration machines and power plants. Quantum computing's influence is amplified when combined with artificial intelligence. AI excels at recognizing patterns and managing datasets, but its algorithms can still run up against the bottlenecks of classical processing. Linking AI with quantum backends allows analysis of broader solution spaces faster, effectively opening up new domains. In energy terms, this hybrid approach is already being tested for molecular design of solar cells, high-capacity storage compounds, and superconducting wires. What once required years of iteration can collapse into days or hours of simulated exploration before lab testing begins. The benefit is not only speed, it is the ability to evaluate options so vast that they exceed classical reach altogether. Still, important limits remain. These devices demand vacuum chambers, shielding from vibrations and temperatures close to absolute zero. They require highly specialized infrastructure costing millions, as well as small teams of experts to operate. For now, they are confined to laboratories and commercial research centers. No regional grid relies on a quantum computer to keep the lights on, and no reactor has switched to designs born solely from quantum simulation. In practical terms, deployment is a generation away at minimum. These machines are still too rare, too expensive, and too fragile to influence industry every day. Yet the direction is what matters. In 2025, quantum prototypes are not abstract demonstrations detached from application. They are running tasks directly tied to energy research. Grid optimization trials, molecular modeling for new materials, and plasma simulations have moved from speculation into pilot results. The trajectory mirrors an earlier era when supercomputers were reserved for governments and elite laboratories. Costs and sizes shrank over time, and capability distributed broadly until once-rare tools became normal infrastructure. Quantum systems are unlikely to shrink as quickly, but the pattern suggests practical access is more a question of scaling than of possibility. In terms of the Kardashev ladder, quantum computing does not add watts to the ledger, but it makes every watt we do generate more effective. It reduces waste through better distribution, increases durability through improved material design, and accelerates fusion development by refining models. The scale is measured in raw power, yet progress also depends on efficiency and control. Quantum's greatest contribution may be as a multiplier, stretching terawatts towards something closer to planetary potential, even before output levels rise by orders of magnitude. The need for such optimization only grows sharper as electrification accelerates. Transport, steel, and chemical industries are moving from fossil systems toward electricity. Digital infrastructure expands constantly, with data centers becoming one of the fastest-growing sources of demand. Without powerful optimization, these shifts burden grids to the point of instability. By identifying pathways through that complexity, quantum approaches could keep growth feasible without collapse. Even if constrained to labs, the insights they yield feed directly into engineering models that shape next-generation energy systems. Of course, expectations should stay anchored. Quantum computers in 2025 are not solving energy crises or replacing gigawatt plants. They remain tools at the edge of practicality. Nevertheless, the precedents set this year show that quantum no longer belongs solely to theory. Real datasets, real optimization challenges, and real physical models are now running through them. Incremental as that may seem, it establishes a foundation on which future scaling builds. In subtle ways, the climb to planetary energy control will rest not just on how much we can produce, but on how intelligently we can structure what we already generate. Quantum computing will not deliver raw energy directly, but if these early steps continue, the technology could make each existing watt far more valuable. That subtle multiplier effect is part of what narrows the long climb to Type I, and as humanity measures its progress in 2025, questions begin to arise about other frontiers. If computation and optimization help us stretch planetary energy further, what might expanding our presence beyond the planet itself mean for our standing on the scale? Space colonization efforts. Does placing humans on the moon or preparing cargo ships for Mars move us upward on the Kardashev scale? The straightforward answer is no. Kardashev's measure records how much energy a civilization can capture and control, not how far its spacecraft travel. A lunar base powered by a few solar panels or compact reactors adds little to humanity's total wattage compared to what a single city already consumes. The value of colonization lies elsewhere, in resilience, in the technologies that must be developed to make it possible, and in the infrastructure that expands the scope of what our species can do. By 2025, these efforts remain symbolic in energy terms, but they are nonetheless central to preparing for later growth. NASA's Artemis program is the most visible anchor of this work. Unlike Apollo, aimed at short-term demonstration, Artemis is structured around lasting presence. Artemis II is planned as the first crewed orbital test of the Space Launch System and Orion spacecraft, verifying the complete architecture before attempting a landing. Artemis III then targets the lunar South Pole, where permanently shadowed craters may hold trapped ice. That water could sustain crews directly or be broken into hydrogen and oxygen to form propellant. Beyond these missions lies Artemis IV, which is expected to introduce parts of a lunar space station, an outpost from which research can be conducted and further surface missions supported. The program is framed not as a national project alone, but as a coalition effort. International partners and commercial companies contribute modules, logistics, and experimental hardware, reflecting the growing complexity of living and working on another world. Alongside Artemis, SpaceX is testing its Starship vehicle, whose design depends on complete reusability and orbital refueling. In 2025, a key demonstration is expected: propellant transfer between two Starship vehicles in low Earth orbit. This maneuver is essential because deep missions cannot rely only on fuel lifted directly from Earth. It would simply weigh too much. Being able to refuel in space changes the economics of lunar travel and opens the path to Mars. NASA's contract with SpaceX to create a human landing system version of Starship links the company's Mars goal with the Artemis framework, ensuring that a single vehicle architecture may underpin both lunar and future interplanetary efforts. Meanwhile, a growing band of private and international missions expands the broader landscape. In June 2025, Axiom Space will launch its AX-4 crew to the International Space Station, led by veteran astronaut Peggy Whitson, and joined by representatives from India, Poland, and Hungary. Their task includes scientific research, technology demonstrations, and testing the commercialization model that Axiom hopes will lead to standalone private stations in the coming years. The European Space Agency brings another layer with its Space Rider robotic laboratory, expected to fly late in 2025. That reusable spaceplane will orbit for 2 months conducting automated experiments before returning intact for refitting and reuse. Together, these projects showcase a shift towards sustainable platforms rather than one-off journeys, lowering costs and embedding reuse and partnership into the core of expansion. From a Kardashev standpoint, the numbers remain unchanged. Colonization efforts still amount to negligible increases in energy control, no matter how dramatic they appear on launch pads. But significance is not measured only by terawatts. Why this matters? The technologies you hear about for living off-world, closed-loop life support, compact reactors, advanced recycling, efficient propulsion, have direct benefits back on Earth. A recycling system that keeps astronauts alive in a sealed base also points toward how to better manage resources in large cities. Nuclear reactors designed to be portable and reliable on the Moon could support remote communities on our own planet. Space colonization therefore functions as applied research under extreme conditions, incubating systems that extend Earth's ability to manage resources. Resilience is an equally important rationale. Kardashev's yardstick does not consider survival factors, but any Type I civilization must remain stable in the face of risk. Confined to one planet, humanity remains vulnerable to natural hazards and its own environmental pressures. A settlement beyond Earth does not yet change the wattage count, but it reduces the odds that a single catastrophe, climatic, geological, astronomical, or self-inflicted, erases the species altogether. In this sense, colonization is an insurance plan. Energy abundance without a safety net would be fragile. Redundancy sets the stage for lasting advancement. The presence of usable resources on the Moon also strengthens the logic. Water ice at the poles offers not only life support, but also a potential way to manufacture propellant locally. Extracting and processing it remains hypothetical, but the promise of launching lunar missions from lunar-derived fuel carries long-term potential for infrastructure building. Even if terrestrial power numbers remain unaffected for now, the concept proves vital. Once colonies begin to tap extraterrestrial resources, Kardashev's ladder will eventually reflect more than a single planet's output. The symbolism cannot be overlooked either. The Apollo era proved humanity could step beyond Earth, but offered no continuity. Artemis and Starship suggest that the next phase may emphasize permanence. Missions shift from momentary demonstrations to architecture that can be extended and reused. Space stations, transport systems, and surface bases provide a framework where continuous activity becomes possible. That change in mentality is as notable as the rockets themselves. Science and industry move from rare appearances in space to something approaching operational presence. There is also the matter of political and cultural maturity. High outputs of energy will not push us to higher classifications if collapse undermines continuity. Colonization supports stability by spreading knowledge, industry, and biological diversity to multiple sites. The Kardashev scale may not score this directly, but from a civilizational perspective, it is indispensable. A Type I civilization resilient enough to outlast planetary scale challenges must develop redundancy before reaching peak energy absorption. Without resilience, wattage records would hold little meaning. By the end of 2025, humanity's Kardashev rating is still tied to Earth's consumption in the range of 18 to 22 terawatts. Colonization has not shifted that baseline. What it has done is build prototypes of the systems that might eventually matter: ice-to-propellant experiments, reusable spacecraft, compact reactors, recycling technologies, and adaptive infrastructure. These seeds will matter later, when scaling off-world industries contributes measurable energy totals. For now, they show that colonization, though invisible in Kardashev's ledger, functions as a rehearsal for resilience, technology transfer, and industrial expansion. And as we continue to look outward, another question inevitably emerges. If humanity is taking its first practical steps beyond Earth, could more advanced civilizations already have reached those stages, perhaps long ago, on worlds that resemble our own? The exploration of distant planets and the search for signs of intelligence take this idea from speculation into ongoing investigation. Exoplanets and the search for others. By 2025, the search for exoplanets has shifted from speculation into a systematic program. Instead of only wondering whether life might exist elsewhere, astronomers now have catalogs of thousands of confirmed planets and the tools to begin asking what their atmospheres, surfaces, and orbits actually reveal. Two instruments have been especially important this year: the James Webb Space Telescope and the European Space Agency's Gaia mission. Webb spends a large fraction of its time probing exoplanet atmospheres, while Gaia has started contributing astrometric planet candidates, such as the confirmed giant Gaia 4b. These missions serve different purposes, but together form a complementary picture: which stars have planets and which planets show conditions worth studying more closely. The Webb telescope, in particular, represents a leap. By separating light that passes through an exoplanet's atmosphere during transit, Webb reveals chemical components with precision unavailable to earlier missions. Gases like oxygen, methane, and dimethyl sulfide are of interest because on Earth they are strongly associated with biological processes. Yet astronomers remain careful. These molecules are interesting but ambiguous. Geological or photochemical sources can mimic biological production. Volcanic activity, ultraviolet radiation, or chemical cycles can generate transient mixtures that resemble biosignatures without requiring life. The priority in 2025 is not to declare life discovered, but to accumulate a detailed survey that helps distinguish natural atmospheres from those that may require more unusual explanations. Gaia, designed primarily to map stars with exquisite precision, added an exoplanet milestone by confirming a large planet through astrometric wobble. The detection of Gaia 4b, 12 times Jupiter's mass, is not a candidate for life itself. but its presence shapes the stability and evolution of nearby rocky planets. Giant planets often control how smaller companions form and whether they survive in stable orbits. That context is essential. Identifying gas giants not only broadens the census of planetary systems, but informs where smaller, more habitable-sized worlds might be quietly orbiting. Among those target worlds, red dwarf systems dominate attention. Red dwarfs outnumber sun-like stars and live for far longer, giving any potential biosphere additional time. Their habitable zones fall close to the star, raising risks from stellar flares that could strip or sterilize thin atmospheres. But some models suggest thicker atmospheres or magnetic fields may help planets retain conditions suitable for water. Current observations are pushing toward discriminating between planets that have likely lost their gases and those whose atmospheres remain intact. A rocky world clinging to its shielding air beneath a quiet red dwarf could represent one of the best candidates for habitability. Data from all these missions feed into the Exoplanet Archive, a continually updated repository that combines the latest orbital parameters, atmosphere models, and contextual information about dust levels or stellar properties that could complicate future observations. What was once a purely statistical estimate, hundreds of billions of possible planets, has narrowed to interactive lists of confirmed worlds and their attributes. This makes the search far less abstract. When scientists ask where life might exist, they are naming specific planets, each with measured radius, orbital period, and probabilities of retaining water. The shift from vague speculation to tangible data represents one of the major scientific transformations of the past decade. It can be tempting to imagine that subtle atmospheric anomalies are already techno-signatures, evidence of civilizations ahead of us. After all, if Webb were observing Earth at industrial maturity, it might detect odd ratios of carbon dioxide, methane, and trace gases that suggest technology. But 2025 has not yielded any confirmed detection of such signals. Claims remain preliminary and open to multiple natural explanations. Earth itself shows the caution required. Geological epochs have produced oxygen spikes, methane surges, and widespread chemical shifts long before humans existed. This means that ambiguous gases are interesting, but never sufficient on their own. Consolidating the record, as of this year, no exoplanet survey has delivered direct signs of technological activity. We have found no artificial transmissions, no engineered structures, no clear industrial pollutants unexplainable by natural processes. SETI programs continue to examine candidate stars for radio or optical signals, and any apparent anomalies so far have lost their intrigue under follow-up scrutiny. This lack of confirmation is frustrating to some, but it also highlights the careful discipline shaping the field. Only results that withstand exhaustive review will alter the record. What missions like Webb, Gaia, and ground surveys have done is sharpen the frontier. Instead of asking whether life might exist anywhere across the galaxy, the investigation now focuses on a subset of nearby rocky planets where temperature ranges, orbital stability, and early atmosphere measurements imply higher potential. Progress, then, comes not from discovery announcements, but from narrowing the scope of where discovery might occur. Each additional atmosphere measured with confidence strengthens that foundation. Even within our own solar system, the challenges of confirmation are clear. The Perseverance rover on Mars has studied rock samples like those from the Sapphire Canyon, revealing organics and hints of long-past water flows. Published in peer-reviewed journals, the findings highlight possible biosignatures, but they are not proof of life. If it takes years of close analysis for samples in our possession to be interpreted cautiously, the interpretation of minute spectral lines from distant worlds is bound to demand even greater care. This analogy emphasizes that the stakes are high and shortcuts tempt unreliable conclusions. For now, thousands of exoplanets crowd the catalogs, dozens of them in habitable zones, a handful with atmosphere data suggestive of complexity. But no matter how compelling the candidates, none yet confirm a living biosphere or an intelligent society. The absence of evidence should not be mistaken for dismissal. It instead refines the probabilities and sets the targets more precisely for telescopes to come. Within the next decade, instruments like the Habitable Worlds Observatory will extend today's survey work and directly image Earth like planets around nearby stars, seeking signatures Webb cannot yet resolve. This expanding ability recasts Kardashev's ladder from a framework applied only to speculative aliens into a map against which real planetary candidates are plotted. Some planets may harbor biology without industry. Others, if they exist, might already have civilizations advanced into Type I or beyond. We cannot yet know which, because silence and ambiguous signals characterize the record. Yet that silence itself is not conclusive. It leaves an open space filled with possibility, one that drives global attention back to the instruments, archives, and surveys, adding pieces month by month. Here lies the deeper tension. Humanity can measure spectra, discover wobbling giants, and catalog rocky worlds, but none of these observations settles the question of whether another intelligence shares the galaxy. The technical achievements of 2025 point toward a sharper map, but they stop short of revealing whether anyone else has walked the path we're tracing on Kardashev Scale. What we hold are clues, not conclusions, hints that something may be there, but no definitive signs. Which raises an essential point. If another civilization is out there, will we recognize its fingerprints? That question remains the line dividing optimism from uncertainty, and it is the line that shapes where the search goes next. SETI, UAPs, and signals. What does the search for other civilizations look like in practice when we turn from exoplanet surveys to signals and anomalies already under scrutiny? In 2025, that question takes the shape of SETI programs, government disclosures of unexplained encounters, and a growing body of interdisciplinary debate about what evidence, if it arrived, would even mean. Together, these efforts illustrate how humanity looks inward as much as outward, balancing technical rigor with the openness to consider unexpected data. The search for extraterrestrial intelligence remains the most established channel of inquiry. Decades ago, SETI relied on individual radio telescopes listening at specific frequencies. Today, broad surveys sweep huge spans of spectrum with far greater sensitivity, assisted by vast increases in computing power. Radio arrays simultaneously sample billions of narrow channels, while machine learning highlights unusual activity that might otherwise look like noise. Optical instruments now complement this, searching for spikes of coherent laser light, signals that could cut across interstellar space in ways radio might not. One area of particular attention has been fast radio bursts, milliseconds-long flashes of colossal energy arriving from cosmological distances. In most cases, astrophysical processes tied to magnetars or neutron stars almost certainly explain them. Astronomers are confident that natural causes dominate. Yet the sheer power contained in each event gives these bursts significance for SETI. FRBs are mostly natural, but their energy makes them natural candidates for careful scrutiny. Researchers search for patterns, repetition, or modulation that might hint at a signal hidden within. Thus far, nothing intentional has been found, but the archives keep growing. The result is not discovery, but infrastructure. With AI combing through petabytes of spectral and temporal data, anomalies that once slipped past analysis are flagged for re-examination by experts and sometimes by citizen science groups. This expanding loop means that even if today's catalogs contain no techno-signature, tomorrow's methods may extract insights retroactively. In that sense, the negative result is not wasted effort. It builds an archive that grows more searchable year by year. Parallel to SETI's steady work, public attention has shifted in recent years to what governments have begun calling unidentified aerial phenomena. Long burdened by stigma, reports have now been addressed in official briefings and select declassified releases. Radar records, cockpit videos, and sensor logs are periodically added into the public domain, with authorities acknowledging that certain incidents defy easy identification. In 2025, the disclosures continue, and with them a change in tone. Governments have released data and acknowledged unidentified encounters. That increases scientific attention but has not produced proof of extraterrestrial technology. In other words, the files indicate puzzles, not conclusions. Because of this change, scientific and policy institutions are investing more seriously in discussion forums. A leading example is the Interdisciplinary Research Center for Extraterrestrial Studies conference scheduled for September 2025 in Wurzburg, Germany. Branded as a joint SETI and UAP event, the conference convenes astronomers, data scientists, sociologists, and legal scholars. Its program spans technical presentations on atmospheric measurement, citizen-run imaging projects, and anomaly cataloging, as well as more unconventional topics like searching for artifacts or reviewing the Helstone Lights campaign. By design, it treats signals and aerial cases as data streams worth collection, even if explanations turn out entirely terrestrial. What sets meetings like Wurzburg apart is their explicit recognition that contact, should it ever occur, would not be a purely scientific event. The program highlights legal frameworks, questions of governance, and the impact on collective identity. The shift of UAP and SETI into interdisciplinary space signals preparedness rather than assumption of discovery. The relevance for viewers is straightforward. Evidence touches not only physics or astronomy, but politics, law, health, and culture. To even contemplate an encounter responsibly, institutions must plan across sectors. While these discussions grow, the astronomical side remains consistent. No Dyson spheres have been detected, no star has shown the unmistakable dimming profile of megastructures, and no galaxies have revealed the infrared waste heat expected if billions of stars were harnessed. Such checks are ongoing, but results in 2025 remain clear. There are still no confirmed Dyson spheres or galaxy-wide techno-signatures. The universe, measured against Kardashev ceiling, continues to look natural. This does not equate to dismissal of anomalies. It means that evidence continues to fall short of the extraordinary thresholds required. Patterns of dimming, once considered candidates, now resolve as orbital dust. Spiral galaxies still look consistent with astrophysical processes rather than energy conversion. Unexplained airborne events may stay unexplained, but unexplained is not equal to alien. The rigorous standard of science treats null results as the baseline, waiting for corroborated, multi-instrument confirmation before raising claims. Still, it would be inaccurate to describe the search as stagnant. Instruments gain sensitivity, archives expand, and collaborations link observatories across continents into integrated campaigns. In Chile, Hawaii, Europe, and Australia, synchronized observations now compare anomalies across different spectra in near real time. Algorithms inspired by genetics research attempt to classify signals according to structural regularities, searching for the equivalent of information fingerprints. Citizen scientists contribute imagery and datasets, while new observatories integrate weather, astronomical, and satellite records to rule out conventional explanations. The cumulative effect is an apparatus more prepared than ever to recognize something unusual, even if nothing yet has met the standard. For UAP in particular, the emphasis has shifted toward rigor without presumption. Some campaigns deploy automated all-sky cameras designed specifically to filter out aircraft or satellites. Others analyze atmospheric conditions and seismic data in tandem, searching for cross-correlation. Work in Norway's Helstone Valley, for example, continues with optical and spectroscopic monitoring of recurring luminous phenomena that defy easy categorization. Such projects exercise the discipline of treating unusual observations as scientific problems without inflating them into conclusions. This more measured approach also acknowledges the psychological element. Human observers are prone to pattern recognition and suggestion. Technological sensors are prone to error and interference. By establishing redundant methodologies, scientists attempt to eliminate human perception traps and technological flaws alike. The principle is simple. A genuine signal or object should manifest in multiple independent records and resist all candidate conventional explanations. Until then, withholding judgment remains the path of credibility. Across all of these threads, what stands out in 2025 is the balance between renewed openness and measured restraint. Astronomers sift signals but remain cautious about attribution. Governments acknowledge mystery but stop short of interpretation. Conferences gather experts from unrelated disciplines because if evidence does arrive, the implications cannot be contained to any single field. SETI and UAP discussions once occupied the margins. Now they inhabit mainstream institutions, without producing proof, but with growing urgency to be prepared if proof ever does appear. So where does all that ambiguity leave us? It leaves us with a disciplined but unresolved search, quiet skies at astronomical scales, tantalizing puzzles at human scales, expanding archives of data across all scales. And just beyond the uncertainty lies the question that pulls every piece together. How long will it take before we, or perhaps some other civilization we detect, make the jump that changes position on Kardashev's ladder? The search defines the landscape, but the clock defines the tension. The next step is to confront those timelines directly and ask what they really suggest about our future path. Timelines to the Kardashev future. So when will humanity finally reach Type I on the Kardashev scale? The question remains unsettled, but it defines how we think about our long-term place in the universe. Estimates available in 2025 suggest that we are unlikely to achieve it within one generation, yet the horizon may be closer than once assumed if current trajectories hold. The simplest way to frame the problem is through growth rates. If global energy use grows at around 2–3% per year, a common scenario used by futurists, then the compounding effect produces striking results. Within this pace, analysts place the arrival of Type I capabilities in roughly 100 to 200 years. This range is not a forecast so much as an illustrative trajectory. It assumes consistent expansion without major setbacks or collapses. Compared to the centuries-long sweep of industrial history, a timescale of 1 or 2 centuries feels tangible. It is the difference between the present and the invention of steam power, a span of memory we can relate to in concrete terms rather than cosmic abstraction. Recent data points help explain why optimism has risen. In 2024, clean power passed 40% of global electricity generation for the first time, a milestone driven largely by record solar expansion. According to Ember's Global Electricity Review, solar added more than 800 terawatt-hours in a single year, the largest increase ever recorded. Wind and hydro complemented this growth, and nuclear edged upward slightly as well. Together, these gains show that humanity can scale technologies at global speed and adopt new sources of power at a scale once thought out of reach. They suggest that the foundations of a Type I economy are not abstract concepts, but systems already under construction across multiple continents. Of course, expansion is balanced by the drag of rising demand. Electricity forecasts from the International Energy Agency in late 2024 projected average global demand growth over 3% annually through 2030, higher than earlier estimates. The reasons are familiar: data centers, cooling requirements in hotter climates, the electrification of vehicles, and industrial shifts away from direct fossil combustion. In practice, this means even record surges of clean power may not immediately raise our Kardashev score. New watts are often consumed just as quickly as they are added. Effective progress toward Type I requires not only building capacity, but also managing growth pressures more systematically. Political and regional disparities make the climb harder to chart. OECD countries, particularly in Europe, show stable or declining demand, while non-OECD states in Asia expand rapidly. Coal consumption has risen again in parts of China, India, and Indonesia, offsetting global gains in cleaner systems. From Kardashev's perspective, these splits slow the overall ascent. Human civilization is not climbing as a coordinated organism. Instead, some regions move upward swiftly, while others plateau or continue burning what earlier centuries relied on. That inconsistency ensures a slower blended trajectory, even if certain nations achieve near planetary scaling earlier than the global average. The environmental constraint may be the most unforgiving. While a strict Kardashev tally cares only about totals, in practice civilization cannot sustain rising outputs if climate damage disrupts food systems, coastal zones, or geopolitical stability. More coal and gas may add watts, but their emissions risk undermining the very progress those watts represent. Hence, energy quality becomes as decisive as energy quantity. An ascent to Type I based on unsustainable practices could collapse long before the scale is reached. In this way, the environmental dimension folds directly into the timeline, imposing strict limits on how humanity can expand. Unbalanced development magnifies dependence on a few major actors. China alone supplied the majority of global solar and wind growth in 2024, installing 278 gigawatts of solar and 80 of wind in a single year. This accounted for most of the world's advance toward more sustainable power. Such concentration means the global trajectory is shaped disproportionately by decisions within a few economies. If they continue scaling aggressively, the timeline shortens. If they hesitate, progress slows for everyone. Kardashev's ladder represents humanity as a whole, but in practice, a handful of nations now build or stall most of the climb. This uneven framework has shaped the cautious estimates that fix Type I at a century or two away. Each gain in renewables, nuclear stability, or efficiency is met by counterforces: surging demand, entrenched fossil reliance, and political fragmentation. When calculated against the daunting requirement of 10 quadrillion watts, the bar for Type I, the climb from today's 20 terawatts still looks steep. The latter reminds us that partial success does not count. Planet-level energy control demands orders of magnitude beyond what we manage now. Yet emerging technologies provide leverage Kardashev himself could not have anticipated. Artificial intelligence now shapes energy distribution with speeds human operators cannot reach, preserving stability and allowing higher penetrations of renewables. Quantum computing, in its experimental form, offers models of materials and optimization routines that expand capacity by increasing efficiency. Fusion, for the first time, delivers sustained reactions long enough to support engineering tests. Together, these tools do not yet alter the wattage total, but they change the slope of expansion, compressing formerly decades-long processes into years or even months. This is the basis for the more optimistic outlook. Under conventional trends, Type I remains a 100 to 200-year project, but layered with accelerators like AI, quantum tools, scalable renewables, and eventual fusion deployment, the climb could contract significantly. It may not reach the science fiction pace of decades, but it could push humanity upward at rates faster than historical energy transitions suggest. The key difference is that, for the first time, multiplier effects operate alongside output increases. Kardashev's scale was drawn as linear. The technologies of 2025 introduce potential nonlinear shifts. That does not mean higher categories of the scale are suddenly near. Type II, harnessing the full output of the sun, remains a multi-century to millennial prospect in almost every scenario. Dyson-like swarms or vast space-based power structures remain closer to speculation than engineering. Still, the principle matters. Once acceleration compounds, the journey to each successive type could shorten relative to the spans once assumed. Optimists argue that Type I might, in turn, hasten the groundwork for Type II. Pessimists caution that even if tools exist, social and environmental constraints may prevent reliable expansion beyond planetary bounds. What emerges from these estimates is less a precise forecast than a pair of plausible pathways. One path is steady and incremental. Global civilization expands its demand by 2–3% annually. Renewable and nuclear supplies scale further. Fossil dependence ebbs slowly, and Type I arrives within about 150 years. The other path depends on acceleration. Fusion matures, AI and quantum shorten timelines, international coordination strengthens, and the climb occurs far faster, potentially closer to a single century. These futures are not guarantees but scenarios shaped by technology, politics, environment, and behavior. The verdict is clear enough to frame how we think ahead. Two plausible futures: steady incremental climb over roughly 100 to 200 years, or accelerated climb if fusion, AI, and quantum systems scale rapidly. That choice defines the uncertainty everyone analyzing Kardashev timelines returns to. Yet one fact runs through all scenarios: greater energy control expands both capability and risk. Kardashev's numbers focus only on opportunity, but every higher level also entails higher stakes. A civilization that manages planetary power must also survive its consequences, otherwise progress collapses under its own weight. And that brings us to the next question: what hidden costs might accompany each step on this ascent? The hidden risks of advancement. The risks that come with mastery of advanced energy systems are as significant as the opportunities. Increasing control over planetary resources widens our capabilities, but each step upward adds new points of fragility. Moving toward Type I means managing planetary scale flows of energy and technology, and with them, vulnerabilities no previous society faced. Progress raises the stakes as much as it raises potential. Environmental stresses rank among the first of these challenges. To move toward full planetary capacity is to push against ecological boundaries. Large-scale harvesting of solar, wind, nuclear, and eventually fusion energy may seem efficient on paper, yet these expansions alter landscapes, affect weather feedback cycles, and reshape ecosystems. Even in 2025, renewable deployment has spurred debates about habitat loss, mining impacts, and resource extraction for rare materials. A civilization aiming to channel all of Earth's usable energy could destabilize its own biosphere through imbalance, making progress fragile rather than secure. Coordinating energy at that scale means knowing that one miscalculated policy or poorly regulated expansion could stress agriculture, climate systems, or entire regions at once. Technology imposes another layer of risk. Artificial intelligence already manages grids and supports fusion experiments at levels beyond human capacity. That reliance also introduces new vulnerabilities. Algorithms trained on incomplete data or unexpected scenarios could mismanage resources, misallocate supply, or even destabilize reactors if errors cascade. These systems may behave in ways opaque to human understanding, leaving little time for correction when things go wrong. A malfunction in an AI-driven grid may not trigger localized outages but could cascade across nations. A failure in fusion oversight, driven by predictive models, could undo years of difficult progress. These outcomes are not guaranteed, but the reliance on tools we do not fully interpret makes them possible. Building transparency, auditability, and governance into these systems is essential. Otherwise, their black box nature becomes a source of systemic fragility. With greater power comes the danger of intentional misuse. Control at planetary scale could shift from being a tool of coordination to a lever of coercion. History demonstrates how the possession of oil or water has driven geopolitics. At a higher rung, electricity itself, communications capacity, or regional energy stability could be deployed as instruments of pressure. Corporations or governments holding concentrated authority over energy systems may find themselves shaping access for billions. The risk here is not inevitable authoritarianism, but the structural temptation power creates. Without robust oversight, fairness erodes and trust, the foundation of social stability, weakens. A society may generate quadrillions of watts, but if the distribution of those watts becomes a tool of exclusion, the scale conceals fragility as much as it displays advancement. Geoengineering demonstrates the same dual edge. The idea of altering the climate directly to counteract warming, by seeding clouds, scattering aerosols, or reflecting sunlight into space, presents a vision of control on par with planetary mastery. But each action carries unintended consequences. Redirecting solar radiation could shift rainfall, causing droughts in some regions and floods in others. Carbon removal at massive scales could disrupt oceans and food chains. Once begun, such interventions are difficult to reverse quickly. On Kardashev's ladder, these acts might look like decisive steps upward, but they may instead tighten dependence and lock societies into brittle systems where even small mistakes cascade into global crises. Artificial intelligence also reshapes risks beyond infrastructure, reaching into personal and social life. Smart grids, predictive systems, and optimization tools log immense quantities of personal and industrial information. Without limits, this data feeds into surveillance capabilities and erodes individual autonomy. The same intelligence that keeps energy distribution stable can be repurposed to track citizens, categorize behaviors, or manipulate outcomes through fine-grained profiling. In parallel, AI tools generate propaganda and misinformation at new scales. Deepfakes, synthetic texts, and automated campaigns illustrate how planetary-scale intelligence may corrode democratic legitimacy. Rising wattage on the Kardashev ladder is meaningless if trust and cohesion decay under pressures of manipulation. A society fractured by automated disinformation risks paralysis just as surely as one starved of energy. Automation and inequality compound this vulnerability. As AI drives energy systems, transport, manufacturing, and industrial processes, traditional employment structures erode. Millions face displacement across industries even as new types of work emerge. Societies unprepared to retrain or distribute resources equitably risk deepening divides between elites who control these technologies and those left behind. Expanding total energy control while excluding significant portions of humanity creates instability. Discontent and inequality erode cooperation, making international coordination, the very thing needed for planetary energy control, less likely. Kardashev's ladder is silent on distribution, but sustainability depends on social fairness as much as sheer output. Weaponization casts an even darker shadow. AI-guided systems increasingly reduce the time for human decision-making in conflict. Drones and automated defenses already highlight how lethal force operates without direct human control. Extending this to future conflicts fueled by planetary-scale energy raises ethical and existential questions. Autonomy in weapons systems diminishes accountability and accelerates escalation. If machines direct life and death decisions powered by planetary resources, wars could spread with unprecedented speed and intensity. These risks show how easily progress could collapse, not through shortage, but through misuse of abundance. The concentration of capability sharpens each of these challenges. As of 2025, the most powerful advances in AI and energy are concentrated within a handful of nations and corporations. This creates a digital divide, with some benefiting from exponential growth and others excluded. The imbalance is not only unfair but destabilizing. Those left behind may resent or resist, and those in control may weaponize their advantage. Fragmentation then replaces cooperation, and the latter becomes less a shared climb than a contest. Such divides risk breaking the very coordination planetary control requires. The overarching lesson is that energy mastery magnifies vulnerabilities alongside expansion. Every watt captured increases reliance on delicate networks, automated systems, and cross-border cooperation. The Kardashev scale measures raw power, but raw power without effective governance is brittle. A Type I society sustained only on physics, without ethics or fairness, would remain precarious. Each rung must be reinforced by transparency, accountability, and trust, or else it risks collapse under the pressure of its own tools. What remedies exist? International governance for shared systems, regulations requiring transparency of AI, protections for privacy and autonomy, and deliberate strategies to share technological benefits more equitably. These are not optional extras, but structural requirements if higher civilization is to persist rather than falter. Transparency and cooperation provide shock absorbers for mistakes and safeguards against manipulation. Without them, each achievement could become a liability masked as progress. What matters going forward is not only the total energy humanity can command, but how we preserve resilience against its risks. Fragility lies not in scarcity alone, but in how abundance is used. Advancement brings hazards of ecological imbalance, opaque automation, inequity, and weaponized control. Meeting these challenges requires cultural, political, and ethical capacity equal to our technical one. The Kardashev scale alone cannot measure these hidden factors, but they are decisive. As global civilization continues its climb, stability will rest not just on the energy totals we add, but on the wisdom we show in managing them. Only then will growth translate into survival rather than collapse. And it is in that balance between capability and restraint that the real challenge of our trajectory now lies, waiting for us to face it directly as we consider our fragile position today. Humanity stands at roughly 0.74 on Kardashev's scale, still far from mastering Earth's full energy. Yet 2025 revealed tangible hints of a path forward. Fusion records, a surge in clean power, and the rise of AI and quantum tools show how our progress may accelerate in ways Kardashev never foresaw. Each of these technologies extends not just output, but control over complexity. 2025 did not push us to Type I overnight, but it placed the building blocks on the table. How we use them will decide the century. Which accelerator matters most? Fusion, AI, quantum, or colonization? Share your view.